law? Well, the Gauss law is um, is present in the study of electrostatics, and Gauss law states that the total electric flux through a surface is the total electric charge inside the surface divided by epsilon sub zero, where epsilon sub zero is a constant, which means the permittivity of free space, and has an approximate value of 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. And the Gauss law shows the relationship between electric field, electric flux, and electric charge. With all of these statements, here is our mathematical expression for the Gauss law. Again, the total electric flux that a particle or a surface will experience is dependent or can be calculated with the total charge that is present that the total charge that is present on the surface divided by the permittivity of free space. So you have here total flux is equal to electric field times your surface area vector cosine angle between your electric field and area vector, which is also equal to the total charge divided by the permittivity of free space. So you have it here, the relationship between flux, electric field, and electric charge. So let's have an example. Basically, the Gauss law, or the surfaces that are described under the Gauss law, is known as a Gaussian surface, and the charges that are present in the Gaussian surface will be the ones that will affect the flux, or that will form part of the flux that flows through that surface. So calculate the total electric flux for each of the closed surfaces A, B, C, and D, as shown below or shown on the right. Note that Q1 is equal to positive 4 coulombs, Q2 is positive 6 coulombs, Q3 is negative 5 coulombs, and Q4 is a negative 12 coulombs. So what do we do here? Again, since your electric flux can be calculated, your total electric flux can be calculated with the total charge divided by the permittivity of free space. We have here 4 surfaces. So for surface A, to start with our problem, what are the charges present in surface A? If this is surface A, the biggest rectangle there, or square, your surface A has all of the charges Q1, Q2, Q3, and Q4. Therefore, the total charge will be Q1 plus Q2 plus Q3 plus Q4. The flux for A is Q1 plus Q2 plus Q3 plus Q4 over the permittivity of free space. And that will be Q1 is positive 4 coulombs plus Q2 is positive 6 coulombs. Well, let's rewrite that one. We have plus positive 6 coulombs plus Q3 is negative 5 coulombs plus Q4 is negative 12 coulombs. So what will be our answer here? So that's positive 4 plus positive 6 plus negative 5 plus negative 12. That will give you negative 7. Well, of course, you need to divide that by the permittivity of free space, which is 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. So what will be our answer here? So you have positive 4 plus positive 6 plus negative 5 plus negative 12 is negative 7 divided by your permittivity of free space, approximately 8.8542 times 10 raised to negative 12. So it will be our answer here. Our answer is negative 7.91 times 10 raised to 11 Newton meter squared per coulomb. So this is the flux, the electric flux on surface A. Now for surface B, we have here this blue rectangle. Oops, let's rewrite that one. We have here the blue rectangle, this one. And what are the charges present on surface B? So if you can see also, it's Q1, Q2, Q3, and Q4 as well. Similar to your surface A. Now, since it also has the 4 charges, therefore your total flux for surface B will also be this one. You will have electric flux for B is also negative 0.7 and negative 7.91 times 10 raised to times 10 raised to 11 Newton meter squared per coulomb. For surface C, that's the triangle here. And what's the charge enclosed in that Gaussian surface? It's just charge 2 divided by permittivity of free space. So that will give us charge 2 is positive 6 coulombs divided by 8.8542 times 10 raised to negative 12 coulombs squared per Newton meter squared. Placing that in our calculators, that's positive 8 divided by 8.8542 times 10 raised to negative 12. So that gives us an answer of 6.78 times 10 raised to 11 Newton meters squared per coulomb as your electric flux. And for surface D, you have this circle. And what are the charges present on the surface? It's Q1 and Q2. So Q1 plus Q2 divided by permittivity of free space. That will give us your Q1 is positive 4 coulombs plus positive 6 coulombs divided by 8.8542 times 10 raised to negative 12 coulombs squared per Newton meter squared. So your electric flux for surface D is positive 4 plus positive 6 coulombs divided by 8.8542 times 10 raised to negative 12. So our answer here, the flux for surface D is 1.13 times 10 raised to 12 Newton meters squared per coulomb. So this is the amount, these are the amount of flux or the total electric flux that flows through the closed surfaces A, B, C, and D. Now we have here charge distribution and Gauss law. The Gauss law can be used to compute the electric field due to a system point charges, as well as for continuous charge distribution. Charge distribution can be expressed in the following terms. We have linear charge density, surface charge density, and volume charge density. By the term themselves, we can describe what these charge densities are. Your linear charge density is your charge per unit length. For surface charge density, the charge per surface area. And volume charge density is the charge per volume, with corresponding formulas: total charge over length, total charge over surface area, and total charge over volume, respectively. So let's have here an example. If a solid insulating sphere of radius 50 centimeters carries a total charge of 150 nanocoulombs uniformly distributed throughout its volume, what is its A, volume charge density? What's the magnitude of the electric field at 10 centimeters and 65 centimeters from the center of the sphere? So it's mentioned here that it's a solid insulating sphere, and remember that when the material is insulating, the charge will be distributed throughout of the volume of the object, or throughout the volume of the sphere in this case. If it's conducting, then the charges will stay on the surface. But since it's insulating sphere, then the total charge, the 150 nanocoulomb charge, will be distributed, uniformly distributed throughout its volume. So question A, we need to solve for the volume charge density, and the volume charge density is your charge divided by volume. So to solve for the volume charge density, we need to, of course, know the formula for the volume of the sphere. Volume of sphere. And what's the formula for the volume of sphere? The volume of a sphere is equal to 4/3 pi radius cube. Now we are using here big R because in our illustration, your big R here, capital R here, represents the radius. Your R sub 1 is the radius for question B, or for the value that we need to solve in B, and R2 is the value that we need to solve for letter C. So we have here now our formula. If we change this expression into the formula for sphere, then volume charge density will be equal to the total charge divided by 4/3 pi r cubed. Then we substitute our values. Since we have 150 nanocoulombs, we need to convert 150 nanocoulombs into coulombs. And that is 150 times 10 raised to -9 coulombs. So you can write it down here, 150 nanocoulombs times 150 times 10 raised to -9 coulombs divided by 4/3 pi. Your radius is 50 centimeters. We need to convert that also into meters, and that will be 0.5 meters cubed. And what will be our volume charge density? So volume charge density will be 2.87 times 10 raised to -7 coulombs per cube. Now, for question B, we need to solve for the electric field at 10 centimeters. So at this point, now looking at our illustration, or with our problem here, this radius here, the 10 centimeters, is inside the sphere. Now, how do we solve for electric field? So we have a formula for electric field where remember Gauss Law, where the total flux is equal to EA cosine theta, which is equal to the Q total divided by your permittivity of free space. Now, our object is a sphere, and in spheres, your electric field and area vector are always parallel to each other, which will cause this to be equal to 1. If we take this expression and get a formula, or derive a formula for electric field, then we have electric field would be equal to Q total divided by the area times permittivity of free space. Now, the question here is, what is your total? What is your total charge? As stated, the total charge of the sphere is 150 nanocoulombs. However, the 150 nanocoulombs is distributed all throughout the sphere. But to solve for the electric field at R1, we need only to factor in the charges that are within R1. But good thing we were able to solve for volume charge density. Because what does the volume charge density mean? This means this answer here, this one, that for every cubic meter, there will be 2.87 times 10 raised to negative 7 coulombs. So we can use this one. We can use the formula for, or we can use our value for volume charge density. So we also need to, we can proceed with our solution if we just change this expression into our expression with volume charge density. If you look at here, if you look at our formula for volume charge density, a volume charge density is equal to charge divided by volume. Deriving an equation for charge, then that will be volume charge density times volume. So that will be volume charge density times volume. And this volume here can be replaced with the formula for the volume of the sphere. And that is 4/3 pi r cubed over our formula for uh, the area, surface area of a sphere, which is the surface area formula for sphere is 4 pi r squared. But since what we are solving here is for R1, so we should make our expressions in R1 so that we don't get confused. So let us rewrite this one so that we are guided accordingly. Pi R1 cubed. Then looking at our expressions, we can cancel out pi, 4, and r, which will give us an expression or a formula: volume charge density, or electric field is equal to volume charge density divided by volume charge density, this is cube, volume charge density times R1 divided by, we have here 3. Of course, we left the permittivity of free space in the previous expression. So that's 3 permittivity of free space. So this formula here for electric field is from the Gauss Law, where we change the expression for Q total and of course, your formula for the surface area of the sphere. Now we can substitute our values. Your volume charge density is 2.87, 87 times 10 raised to negative 7 coulomb per meters cube times your radius. Your R1 is 10 centimeters, so that's 0.10 meters over 3 times 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. So our electric field at R1 will be equal to, if you input that in your calculator, that will be 1080 newtons per coulomb. So that's the electric field at R1. So at radius 1, or at 10 centimeters, the electric field is 1080 newtons per coulomb. Now, for letter C, it's 65 centimeters from the center of the sphere. So for C, we will use R2, which is 65 centimeters. Now, unlike R1, R1, R2 is outside the sphere. And when you look at it, the total charge, which is 150 nanocoulombs, is entirely enclosed in R2. Therefore, to solve for the electric field at R2, we can simply use your formula total charge, the one that we derived in the previous problem, which is problem B. Your electric field is equal to Q total times area permittivity, Q total divided by area times the permittivity of free space. We don't need to express this in volume charge density because we know that the total charge will be equal to 150 nanocoulombs because the entirety of the charge of the sphere is enclosed in R2. So what we need to change expressions here is just the formula for the surface area of the sphere. So that's the total charge is 150 times 10 raised to negative 9 coulombs, which is equal to 115 nanocoulombs, divided by the formula for the surface area of a sphere is 4 pi. The radius is 0.65 meters squared times your permittivity of free space, which is a constant. So this is the value. We have coulomb squared per Newton meter squared. And then when you input that in your calculator, your electric field will be 3,191 newtons per coulomb. So the electric field at 65 centimeters is 3,191 newtons per coulomb. Now, as I mentioned earlier, for this case, it's an insulating sphere. But what if it's a conducting sphere? If it's a conducting sphere, the charges, the 150 nanocoulombs of charges will be concentrated at the surface of the sphere, which will make calculating for volume charge density nonsense because the sphere does not have charges in its entire volume, but instead it only has charges on the surface in the case of conducting spheres. And if that's the case, then the best charge distribution that we could solve is the surface area density or surface charge density. Now, if it's a conducting sphere, there will be no electric field within the sphere because there are no charges within the sphere. All of the charges are outside, or all of the charges are on its surface. So you need to remember that as well. So that's it for our lesson on Gauss law. Basically, the Gauss law again shows the relationship between electric flux, electric charge, and electric fields. So thank you very much for listening.